Alright, sublimation. So this is a process that actually happens quite a bit and we don't even really realize it. But this is when we have solid going directly into the gas phase. The opposite process is what we call deposition. This is when we have a gas going directly to solid. And both of these things actually happen quite often. Sublimation, though, is slow enough that you usually don't see it happening very quickly, but you might notice, like if you have some ice in your freezer that's been at the bottom of the ice tray or the bottom of the ice bucket for months and months, and you might notice there's a whole bunch of holes, and like that, those pieces of ice are really frail in a sense, like they're missing a lot of material. That's sublimation. You had water molecules that escaped the solid phase. They did not turn into a liquid, because if they did, then they would have just refrozen. Instead, they directly went into the gas phase, and that's how they escaped. And again, deposition is just the opposite of that. One thing that I do want to point out about this is that deposition and sublimation are processes that can only occur at the edges of material. So it's kind of similar to what happens with the vaporization. Melting and freezing is not quite the same way, but with sublimation, if you have a solid piece of ice, the water molecules can't escape if they're right in the middle of the crystal. They might try to go into the gas phase if they're right in the middle of the crystal, but they would be very quickly recaptured. They would lose that energy that they had and go back to being a solid. So this really only happens right at the edge of the crystal. Melting and freezing, we're going to spend a little bit more time on this one than the sublimation. This is one that you are much more familiar with than sublimation and deposition. Very similar to vaporization and condensation, we can find what we call the heat of fusion for this process. So for vaporization, we had heat of vaporization. For melting, we call it heat of fusion. I'm not actually entirely sure why it's called that. It's more of an old-timey name. If you don't want to call it the heat of melting, I wouldn't yell at you. But the heat of fusion is just the exact same thing as heat of vaporization, just for melting instead of for the vaporization. Couple quick things that I want to point out about this is that the heat of fusion is almost always, and I only caveat that because there are exceptions to practically everything, but in every case that I am aware of, the heat of fusion is smaller than the heat of vaporization. It takes less energy to melt something than it does to vaporize it. And like I said, I'm not aware of any exceptions to that, but you never know. There's exceptions to practically everything. But for our purposes, we're going to pretend like there are for sure no exceptions to that. And this should make sense, because if you're going from the solid phase into the liquid phase, you're still maintaining the vast majority of the intermolecular forces that the molecules had when they were in the solid phase. Because they're still really close to each other, they're still bumping into each other very often, lots of contact. So the vast majority of the intermolecular forces are still present, but when you go into the vapor phase, into the gas phase, now all of a sudden you have very, very little intermolecular forces. All those intermolecular forces that you had before in the liquid phase had to be broken to get that to go into the gas phase. And so it takes a lot more energy to vaporize something than it does to melt it. And by the way, what this right here is pointing out is that whatever amount of energy it takes to melt a material, which is what the heat of fusion is, the amount of energy that you have to pull out of a material to freeze it, which you would call the heat of crystallization, it's going to be the exact same value, just opposite in sign, as the the heat of fusion. Essentially, if the material has this much energy when it is a liquid, when it's melted, and if it starts off as a solid here and you melt it, so this distance here is the heat of fusion, well then if you're going to refreeze it, it's not like it has to go to a lower energy to do that, it's just going back to where it was before. So the heat of crystallization is just the exact same value, opposite in sign. It's like saying, you know, it takes me 10 footsteps to go to my kitchen, you know, but it takes me 15 footsteps to get back to my seat. Well, that doesn't make any sense. It's the same distance. So that's just all that's getting at. All right. And we've already talked about the heating curve of water a good bit there, but this is just pointing out something that we discussed earlier, which is you can see the differences here. So the difference between the heat of vaporization and the heat of fusion, you can see that in the distance here. That's why those are so different in size, because it takes more energy to vaporize. All right, let's do a real quick practice problem here. And then we'll, I think we'll just call this a really short video here, and we'll move on to phase diagrams in the next one. So this question asks, how much heat is required to convert 135 grams of ice at negative 15 degrees C into water vapor at 120 degrees C? Oh, and I said this was going to be a real fast and quick one. This is actually not a real fast and quick one. It's not super long either, but it's more than one calculation, which is what I thought it was when I first saw it. But this is multiple calculations, actually, because we're starting with ice at negative 15, and we're going all the way up to gaseous water at 120. So why don't you go ahead and try this problem out on your own first, but I will give you a quick hint here. You're going to need that. Hopefully you recognize this equation from Chem 1. This is, well, there's different names for it, but this is the equation that relates energy and the specific heat and the change in temperature of a sample. So you will need this for this question. So go ahead and pause the video, try to work this out on your own, and then come back and see if you got it right. Alright, so the first thing I'm going to do here is I'm going to map out what I'm going to be doing, because I'm going to have, I believe, 5 different small calculations. So all of them together are not a small problem, but each individual part is fairly small. I need to figure out how much energy does it take to go from ice at negative 15 degrees C up to ice at 0 degrees C. Then I need to figure out how much energy does it take to melt it into liquid at 0 degrees C. Then I'm going to figure out how much energy does it take to heat that water up to 100 degrees C, because that's where it would then vaporize. And then I'm going to figure out, okay, after I, well, actually, then I'll need to figure out how much energy does it take to vaporize it. And then I can figure out, okay, going up then from 100 degrees C to 120 degrees C, how much energy would that take? So there are 5 different sections, essentially. We're essentially working through this graph here. We're saying how much energy did this take, how much energy did that take, and then we heat it up. How much energy did that take? How much energy does it take to vaporize it? And then we heat it up a little bit more. So we're kind of working our way through a heating curve like this. So the first thing I'm going to do is figure out how much water do I have, because this mass here is going to be useful for this equation, but for the heat of melting and the heat of vaporization, I need a number of moles. So 135 grams if I convert that to moles, that is going to be, oh, I don't know, something like 7 moles, something like that. 135 divided by 18.02, 7.5. Okay, so 7.49 moles of H2O. And so using that, I can work out 2 of these sections here. I can work out how much energy does it take to melt it, and how much energy does it take to vaporize that sample. Because it's just going to be this number of moles times those 2 heats, those heats of vaporization and heats of fusion. So for the vaporization, I happen to remember that it is 40.7 kilojoules for every 1 mole. And so if I just multiply my number of moles times that heat of vaporization, I get 300, and we'll say 305 kilojoules. It's 304.9, but we'll round it up because we only have 3 sig figs there. For the fusion, for the melting, I actually don't remember that off the top of my head. That is 6.02. So it is 6.02 kilojoules for every 1 mole. So once again, if I just multiply this by the number of moles I have, that will tell me how much energy it took. And it took 45.1. Oops. It would help if I wrote it correctly. Not 451. 45.1 kilojoules. Alright, so that's 2 parts. Now I have the rest of the temperature change values here. So I am actually going to have to look up a value here real quick, because I do not remember what the specific heat of gaseous water and solid water are, because those are different than liquid water. So I'm going to pause the recording so you're not going to see me doing this, because I don't want you to just watch me strolling through my internet browser looking for that, but I will come back when I find those numbers. Okay, so I apologize for the screen changing like that. I forgot that when I exit my PowerPoint slides, it deleted the annotations, the markings that I had made, so I had to write some of this stuff back down again. But this was the value, the amount of energy that it took to vaporize. This was the amount of energy that it took to melt. And I was going to look for these numbers here. So this is the specific heat of ice. It is 1.99, or actually, sorry, that's the number for steam. It was 1.996 joules per gram degree C. The value for ice was 2.11 joules per gram degree C, and you might remember from Gen Chem 1 that the value for liquid water is 4.184 joules per gram degree C. So you can see that you might have been able to get away with using just 2 for each of these, but they are nowhere near the value for liquid water. So we can't just insert the number for liquid water for the other 2. It would have given us an incorrect answer. So then the last thing we need to do here is 3 of these calculations, because we have 3 different temperature changes that take place. So we are looking for Q in each of these, how much energy it took. In each of them, we have 135 grams The specific heat is going to be different for each one, so we'll just do ice, liquid, and then steam. So the ice is 2.11 joules per gram degree C. Liquid is 4.184 joules per gram degree C. And steam is 1.996 joules per gram degree C. And then the delta T's are going to be different for each of them as well. Remember that delta T is the final minus the initial. So, for the ice, it started at -15 and went up to 0. So that is going to be an increase of 15 degrees C. For the liquid water, it goes from 0 to 100. So that's 100 degrees C, delta T. And then for the gas, it goes from 100 to 120. And so that is 20 degrees C, is its delta T. So if I do these calculations, okay, lots of calculator work. This first one here, I'm going to go ahead and convert it to kilojoules. This is 4.27 kilojoules. My calculator gave me 4,272, but it's 4.27 kilojoules. The next one here is going to be the biggest. This is 56.5 essentially kilojoules. And then the next one, and the last one, is 5.39 kilojoules. And so then the total energy that is required to heat water, to heat 135 grams of water from -15 degrees C up to 120 degrees C is all 5 of these added together. So that would be 5.39 plus 56.5 plus 4.27 plus 45.1 plus 305, 416.3 essentially kilojoules. All right. It's a lot of energy. But again, that is the energy, that is all of this essentially. That's that whole amount of energy that took here to go from solid, melt it, increase the temperature, vaporize it, increase the temperature some more. All right. We'll talk about phase diagrams in the next video, so I'll see you there.